In 1891, Nikola Tesla gave a lecture in New York. This essential lecture holds the key to understanding many of his mysterious demonstrations of what he later called radiant energy. He explained and demonstrated in the lecture the disruptive discharge of the capacitor, which produced the current impulse. In this video I will share quotes from the lecture and explain the principles using my VR 3D whiteboard. I will also give a demonstration with an experiment. Hi, my name is Ivo and I've been doing open source research for the past 8 years, sharing the gained insights in the videos on this YouTube channel. So you can all learn and benefit from them for free. My previous video experiment did not produce power. When loaded, the impedance changed and the current dropped, so no real power was available. But Nikola Tesla talks about impedance effects from his disruptive discharge. So this might hold the key to unlocking the electric power that is needed so hard on this beautiful planet. Let's continue to the lecture. Experiments with alternate currents of very high frequency and their application to methods of artificial illumination. Nikola Tesla delivered this lecture before the American Institute of Electrical Engineers at Columbia College, New York, May 20th in 1891. That's a long time ago, 133 years ago. And still we don't get it. So, let me explain a little bit more about this essential lecture about the powerful electrostatic effects which Tesla used to get his magic working. First, the introduction. Nature has stored up in the universe infinite energy. The eternal recipient and transmitter of this infinite energy is the ether. The recognition of the existence of ether and of the functions it performs is one of the most important results of modern scientific research. The assumption of a medium pervading all space and connecting all gross matter has freed the minds of thinkers of an ever-present doubt. It has been a great step towards the understanding of the forces of nature and their multifold manifestations to our senses. Now, there's a whole part that I'm going to skip through because I want to get to the essential part of this lecture. The lecture deals mostly with the production of light. It's 1891. They are using electricity now, and he has found a way that is very unique, and that is completely vanished from our field of interest, maybe because we don't understand how it worked, but I think he's pretty clear, so I'm gonna skip all that stuff about lightning, but it is the way he did it with electrostatic effects. So electrostatic fields, we know them from when we pull our sweater off and you get the crackling noise. That's electrostatic. It can manifest in materials that are isolators, that can be polarized, but also conductors can produce electrostatic fields. Conductors can be polarized very easily and very quickly, and that's exactly what he did. He built up an electrostatic field around a conductor by providing it gradually a very high voltage, which built up that electrostatic field. And then he suddenly discharged that electrostatic voltage through a spark gap. That's the whole principle. And he's explaining it clearly in his lecture. So let me go on. Many have been carried away by the enthusiasm and passion to discover. But in their zeal to reach results, some have been misled. Starting with the idea of producing electromagnetic waves, they turned their attention perhaps too much to the study of electromagnetic effects and neglected the study of electrostatic phenomena. Naturally, nearly every investigator availed himself of an apparatus similar to that used in earlier experiments, but in those forms of apparatus, while the electromagnetic inductive effects are enormous, the electrostatic effects are excessively small. Yep, that's what I'm missing. Now he talks about the Hertz experiments. And those are electromagnetic induction experiments. And he says the static effects may be considerable, but only qualitatively so, not quantitatively, since their rise and fall is sudden and since their frequency is small. In neither case, therefore, are powerful electrostatic effects perceivable. Basically, he talks about a voltage impulse from a coil. I worked with those for years, and I found out that that's not the way to go if you want electrostatic effects. A voltage impulse from a coil, an inductive spike, or often called back EMF, goes up and down in voltage. And I explained that in another video, that the displacement of energy then goes back and forth. And he says it won't work that way. Let's continue. When a high-tension induction coil operated by currents alternating only 20,000 times a second has its terminals closed through even a very small jar, and a jar is a capacitor, practically all the energy passes through the dielectric of the jar, which is heated, and the electrostatic effects manifest themselves outwardly only in a very weak degree. Now, I showed you that in my previous video, where I used paper as a dielectric between my capacitor plates, which are coils. And that paper heated up to around 50 degrees Celsius from a high voltage source. So yeah, there goes my electrostatic effect. And so I already came to the conclusion that that paper isn't gonna work. I'm losing my energy there. That's not the way to go. Better is using air. Best, and he talks about it later, is a vacuum. Now, let me remind you that a vacuum is full of ether. And ether is just another word for energy. So the vacuum is not empty, it is full of energy. Next bit. But powerful electrostatic effects are a sine qua non of light production and the lines indicated by theory. And sine qua non means essential. So he says electrostatic effects are essential. Electromagnetic effects are primarily unavailable for the reason that to produce the required effects, we would have to pass current impulses through a conductor. So he talks about using current impulses. Well, I made a video about that. A current impulse is a singular change, a unipolar change in voltage. And when does that happen? It is with the discharge of a capacitor. So current impulses, capacitor discharge, we need a static field, electrostatic field. That means we need a high voltage capacitor. Long transverse waves cannot apparently produce such effects, since excessively small electromagnetic disturbances may pass readily through miles of air. Such dark waves, unless, and that's electromagnetic waves, unless they are of the length of true light waves, cannot, it would seem, excite luminous radiation in a Geissler tube. And the luminous effects which are producible by induction in a tube devoid of electrodes, I am inclined to consider as being of an electrostatic nature. To produce such luminous effects, straight electrostatic thrusts are required. These, whatever be their frequency, may disturb the molecular charges and produce light. Since current impulses of the required frequency cannot pass through a conductor of measurable dimensions, we must work with a gas. And then the production of powerful electrostatic effects becomes an imperative necessity. It's so interesting to me because he says straight electrostatic thrusts are required. An electrostatic thrust. He's talking about electrostatic thrust. Okay. Thrust does remind me of my own experiments with electrostatic thrusts. The field propulsion video shows this effect. And that video also demonstrates that same current impulse, a slow charge of the voltage and a very abrupt sudden discharge of the voltage. And I demonstrated in that video that if a capacitor is used, then that capacitor is set in motion by that powerful discharge, which produces that longitudinal thrust. I'll include the link in the description below to that video. Okay, we go on. Now it comes. Electrostatic effects being dependent upon the potential and frequency to produce the most powerful action, it is desirable to increase both as far as practicable. It may be possible to obtain quite fair results by keeping either of these factors small, provided the other is sufficiently great, but we are limited in both directions. So voltage and frequency. It might be thought at first that if the bulb containing the filament or button of refractory material be perfectly well exhausted, that is, as far as it can be done by the use of the best apparatus, the heating would be much less intense, and that in a perfect vacuum it could not occur at all. This is not confirmed by my experience, quite the contrary. The better the vacuum, the more easily the bodies are brought to incandescence. And this result is interesting for many reasons. First, he goes on explaining how it all works, that he uses electrostatic fields and uses these alternating electrostatic fields to speed up the air molecules that bump into the filament and produce the light. And then he goes on like, yeah, well, actually, in a vacuum, no air molecules, it is more easily to produce the light. Whoa. Yeah. Okay, next one. The matter in the globe being radiant, the molecules would move in straight lines. He already talks about radiant matter. That's really interesting, because this is really at the start of his research into radiant energy, and radiant matter is the movement of the matter that is electrostatic. So, and he says the molecules move in straight lines. So that's a longitudinal motion. But he also referred to the vacuum. Then he says, an interesting thought in connection with such a lamp is that in it, electricity and electrical energy apparently must move in the same lines. Longitudinal. Electrostatic lines that change in potential move in longitudinal ways. It's beautiful. Now he starts talking about the disruptive discharge. Such lamps have been operated by me with current impulses of the enormous frequencies obtainable by the disruptive discharge of condensers. So what he says is you need high voltage for an electrostatic inductive effect. If you want to go low voltage, it won't work. And what is low? Well, in the modern terms, high voltage starts at 1000 volts. And in my experience, it starts working around 4000 volts that you will see some effect of it. But actually 20,000 volts, yeah, you're getting electrostatic effects. You will notice them. Another few pages further on. If a tube be lighted at some distance from the coil and a plate of hard rubber or other insulating substance be interposed, the tube may be made to go out. So he has a coil with electrostatic effects. He has a bulb that is luminescent from that electrostatic induction, and you put in dielectric material like rubber between it, it diminishes. That would not happen with electromagnetic induction. The interposition of the dielectric in this case only slightly increases the inductive effect, but diminishes considerably the electrification through the air. In all cases then, when we excite luminosity in exhausted tubes by means of such a coil, the effects is due to the rapidly alternating electrostatic potential. And furthermore, it must be attributed to the harmonic alternation produced directly by the machine, and not to any superimposed vibration which might be thought to exist. Such superimposed vibrations are impossible when we work with an alternate current machine. Now, what are superimposed vibrations? Such superimposed vibrations are impossible when we work with an alternate current machine. If a spring be gradually tightened and released, it does not perform independent vibrations. So if you have a spring, you compress it, you release it gradually, then it doesn't perform independent vibrations. For this, a sudden release is necessary. So you compress a string and you let it go. So with the alternate currents from a dynamo machine, electromagnetic induction, the medium is harmonically strained and released. And the medium is the ether, the energy surrounding the experiment, the coils. This giving rise to only one kind of waves, electromagnetic waves. A sudden contact or break, or a sudden given way of the dielectric, as in the disruptive discharge of a Leyden jar, are essential for the production of superimposed waves. How clear can he be? Why didn't nobody get this? Or why didn't I why didn't I get this? I've been so many years working at it. It's not electromagnetic at all. You can use it, of course, and probably it is needed for the production of electric power. That's what I'm talking about. But that's what I'm after. To be clear, that's the goal of all my experiments, to find out how to do that and share it with you, so we can all benefit and go to the next level of our world. It's about time, isn't it? 133 years later. Okay, let's continue by using a powerful, rapidly alternating electrostatic field. So that is not a normal form of resonance. Next page. In such an electrostatic field, interesting phenomena may be observed, especially if the alternations are kept low and the potentials excessively high. In addition to the luminous phenomena mentioned, one may observe that any insulated conductor gives sparks when the hand or another object is approached to it, and the sparks may often be powerful. That's pretty fun to watch, I think. So he has a room with coils, and he has induced them with the electrostatic by the disruptive discharge of a high voltage capacitor, single change of voltage, and the coils become electrostatic resonant, let's call it that way, because I'm not sure if it's the longitudinal magneto-dielectric mode, but it makes sense. So LMD, and then inside that field, everything becomes electrified from the electrostatic field that is changing rapidly. Very high voltages he mentions, and a low frequency. This is also interesting. It is true, the electrostatic effects diminish nearly with the cube of the distance from the coil, whereas the electromagnetic inductive effects diminish simply by the distance. So this is generally accepted and known, but he says, when we establish an electrostatic field of force, the condition is very different. For then, instead of the differential effect of both the terminals, we get their conjoint effect. What? The electrostatic field of force? Okay. He is using that electrostatic induction from the disruptive discharge. So actually, he is talking about a dynamic effect, and that cumulative wave, that superimposed wave, is from that single direction discharge. Now, it's interesting to think about which polarity to discharge, because we can discharge from positive to 0, or we can discharge from negative voltage to 0. There is a difference there, and he has referred to that. The apparatus must be capable of producing high electrostatic potentials changing in value with extreme rapidity. High frequencies are especially wanted, because then you can keep the potential a little bit more down. But still you need high voltages. In the disruptive discharge, we have most generally a fundamental instantaneous variation of comparatively low frequency and a superimposed harmonic vibration, and the laws governing the flow of currents are not the same for both. So what he says is, if you discharge a capacitor in a normal way, not disruptive, then you will have oscillations and you get electromagnetic radiation, the dark energy he talks about. And he says, well, actually, that's not going to work, because you need a disruptive discharge. You need a discharge that is unipolar. So slow charge up and then a fast discharge, but no oscillations. And what then happens is that the electrostatic field surrounding that primary, which has that discharge of voltage, as an energy force field being projected from it, and that provides the accumulative superimposed waves in the secondary. The current impulses may be of any desired frequency. When the currents charging the condensers are of the same direction, so DC, and it is desired that the converted currents should also be of one direction, the resistance of the discharging circuits should, of course, be so chosen that there are no oscillations. He says the resistance of the discharging circuit should, of course, be so chosen that there are no oscillations. That's a bit weird. I came to the conclusion that his discharge circuit, so is the spark gap and the capacitor and the stout copper bar. Here he says, with that hairpin circuit, in operating devices on the above plan, I have observed curious phenomena of impedance, which are of interest. And then finally, but there is a possibility of obtaining energy, not only in the form of light, but motive power and energy of any other form in some more direct way from the medium. And the medium is ether, energy. We are whirling through endless space with an inconceivable speed. All around us, everything is spinning, everything is moving. Everywhere is energy. There must be some way of availing ourselves of this energy more directly. Then, with the light obtained from the medium, with the power derived from it, with every form of energy obtained without effort from the store, forever inexhaustible, humanity will advance with giant strides. The mere contemplation of these magnificent possibilities expands our minds, strengthens our hopes, and fills our hearts with supreme delight. And that's the conclusion of the lecture of Nikola Tesla in 1891 in Columbia College, New York. For me, it's very clear. He is so clear. It's an electrostatic effect, and it comes from the change in high voltage on the primary. And the change in voltage is unipolar. It's a current impulse, not the voltage impulse that I used so long. Yeah, I had to learn. Well, there it is. I hope you read it, and I hope you will enjoy what you read and use it to your benefit. I will. Now let's jump into VR and let me explain to you how these concepts work with the electrostatic field. This red part here is a conductor, and I've connected it to a positive 20,000 volts DC. What this will do is create these electrostatic lines of force. They connect this conductor to the surroundings with an electrostatic field. You can see this as a polarization of the ether. These lines are perpendicular to the conductor. So this is the static dielectric field. If I now connect that conductor and source of that positive 20,000 volts to a high voltage capacitor. So I connect the line to this plate, and let's assume that this plate is earth grounded. Then these lines of force, this electrostatic field, becomes dynamic. It becomes a displacement current. And these lines, the electrostatic field, will move along that line into that capacitor. So it now starts to move transverse because the field line is in that direction, but it moves sidewards. And it moves sidewards into this capacitor, and it moves in a transverse manner. So now we have a situation that here is the same 20 kilovolts as is on that conductor over here. So there's still an electrostatic field around the conductor, but now it also charged up that capacitor. So this is the positive plate and this is the earth grounded plate. So that 20 kV source provided that electrostatic energy, that high voltage, and it moved sideways around the conductor into the capacitor. Now we can repeat that same thing if we, for instance, remove that 20 kilovolt source and connect here a coil to ground. Then basically we have a shortcut to this plate through that coil. So that electrostatic field, which has a 20,000 volt potential difference between the plates, is now shorted out through that coil. So again, these electrostatic lines of force will move transverse through this coil. And by doing so, they will take along with it volumes of ether. That is how J.J. Thomson described this in his Electricity and Matter book. And it's all based on Faraday's theory. So these lines of force take with them a volume of ether that is being displaced. And because it's swirling through this coil to ground, this coil will then produce a magnetic field around it, which basically is a swirling volume of ether. Now what Tesla did was not make a magnetic field in his primary. He didn't use the magnetic field. He used the electrostatic field to discharge everything. So back to this situation, we have a high voltage source and the capacitor is charged, and we have that single turn primary here. It isn't even a primary, but let's just take this rod as an example. If we now connect it to ground again, but this time not through a coil, so no inductance, then that 20,000 volt is suddenly discharged. And you would think that they would move sideways again, but it doesn't do that. This time, because the discharge is so rapidly and so fast, it is discharging in the direction of these lines of force, and it creates a longitudinal pressure field, So it expands from all the directions in case of a positive 20 kV. If this was a negative 20 kV, then the discharge would go in the other direction. Then the longitudinal field would be an implosion field into the conductor. So then the field around it collapses inward, and that is if this is negative. So you have a volume of ether that is polarized, that is connected to that conductor, and if it is discharged through a non-inductive path, so not a coil, then you get a sudden change in the electrostatic field that moves along the direction of those field lines, of those electrostatic lines of force, inwards or outwards depending on the polarity. And it creates a expanding field of force or a contracting field of force, an implosion or an explosion of energy. And it is perpendicular to the conductor. The coil and the electrostatic energy, which is built up around that coil, is not moving sideways anymore, transverse, but with the longitudinal static mode, it moves outwards and inwards depending on the polarity change of the voltage. When it goes from positive to negative, it goes outwards, and when it goes from negative to 0 or positive, it goes inwards, like so. 20,000 volts is a lot of volts. This means you will have to work with spark gap, and Tesla was very clear, you need a quenched spark gap so that it doesn't oscillate on the primary. You want a single buildup of voltage and a fast discharge, like so. If you have the axis here, then the voltage this way, positive, will slowly build up into the capacitor, and then fast discharge without change of polarity. So 0 and positive voltage and time. You could also do this in a negative sense. Then you have negative voltage and the time axis. A negative voltage builds up, and then it is suddenly discharged back to 0. And this quick discharge causes that electrostatic movement to be longitudinal, so perpendicular to the conductor. Now we're going to take a look at the electrostatic resonant mode. Red again is a piece of the conductor of the resonant coil, and green is the electrostatic field when resonant. So in this phase of the resonant mode, the electrostatic is maximum. We have pure voltage, and the electrostatic field has been built up around the conductor, which is a polarized ether field. Now, with transverse electromagnetic resonance, these field lines move sideways. And when moving sideways, they drag along ether. And this ether is then moving in a vortex, and that vortex becomes stronger and bigger and larger in volume, and this swirling vortex is the magnetic field. Let me draw it in. So the static field moves sideways, can move both directions depending on the polarity of the transformation, and then the ether is swirling around it like so, and that is the magnetic field that is being built up. Then the electrostatic lines of force diminish in their amplitude, in their volume, in their power, in their energy, and completely transform into the magnetic field, which is that swirling volume of ether. So that is the traditional resonant mode, which we can observe with the normal Tesla coils of today. But Tesla did it differently, as I explained. He used electrostatic induction, creating an electrostatic resonant mode. This electrostatic resonant mode has no magnetic field and no transverse movement of the electrostatic field. Instead, the electrostatic field moves out of the conductor or into the conductor. So it changes amplitude again, but it does this in a stationary electrostatic position. So this means that the force field now is expanding or contracting, like an explosion or an implosion. This creates a different rotation of the, I want to say magnetic field, but this time it is not a magnetic field as there is no swirling action. What now happens is different, and I can best explain it by looking at a donut. Okay, here we have a torus, a ring toroid, a donut. So it has a hole in the center and it's a circular shape. Now, this is a representation of a flow direction of the ether. So here we have a ring vortex. When it is magnetic, these energy flows around that ring vortex in a certain manner which is under an angle, like this. So the diameter of the ring is like so, but it doesn't move in this way. It moves a little bit under an angle. And that is the magnetic field. And this creates that twisting because it is twisted in its nature, because it's everywhere moving inwards like so. So you have an influx of energy that is circulating around. So this would be a north pole and that would be a south pole, depending on the flow direction. And this is due to that electrostatic field moving sideways. That causes that angle of the magnetic field moving over it. So if we now have a movement which is stationary, then the energy moves in the circular manner, which is just closed loop around that toroid. And then you have a different energy flow. It is closed looped, as I said. Oh, sorry, those arrows are wrong. So I draw an arrow here, and the energy is now moving inwards like so. The fact is that the electrostatic lines now build up in amplitude and diminish in amplitude. And when it diminishes in amplitude, it creates this ring vortex. So you could say the conductor is here in the middle, and the electrostatic lines of force would be perpendicular, like so. And these thus do not move up and down, but only extend and contract on the same position. And this is what Tesla called a stationary resonant mode. So stationary waves are like this, while if it is not stationary, if these electrostatic lines move along that conductor, then this will not be a closed-looped field which is built up. Then it becomes at an angle around that ring toroid. And then it is magnetic because now it is moving the energy. It is swirling around, and that movement is from the movement of the electrostatic lines of force which drag along the ether. So to be clear, these grow and diminish in size, and this also grows and diminishes in size. When this field is completely zero, then the electrostatic field is at its maximum, then it's completely polarized. And when this electrostatic field is completely diminished, then this ring vortex field, which moves circular on itself, is maximized. So if you have a coil in an electrostatic resonant mode, you have that ring toroid field and you have the stationary movement of that electrostatic field. This will have a very high resonant frequency. You can put a capacitor over that coil and tune it down in resonance. This will also cause it to reduce in voltage and increase in current, but it changes the frequency. And by changing the frequency, this electrostatic mode won't be able to happen anymore. When the frequency is dropped, then the movement becomes transverse again until you reach the perfect harmonic of that electrostatic resonant mode, of that frequency which was happening without that capacitor. So when you add a capacitor, you will have to take care of those leads that they are already present in that electrostatic mode, because they will be part of that resonant mode. And then when you tune that capacitor, you need to tune it to a frequency which is a subharmonic of that resonant frequency, and then the electrostatic field can be moving longitudinal again without having that transverse motion, so that again you get this ring vortex. If you do not tune it correctly, then this won't form, but the transverse movement will again create that swirling magnetic field again, which has different properties. So tuning is very critical. First, you need to know what is the base frequency of that electrostatic resonance caused by the disruptive discharge. And then when you know that frequency, you can add capacitance and tune the system to a lower frequency. At the same time, that electrostatic field will diminish due to the increased capacitance. You still need that electrostatic field. Okay, I got this setup here that I want to show you. It's a 12-volt battery right here, which powers this ZVS driver. And this ZVS drives this flyback transformer. So this makes DC high voltage. And I connected the negative side up to this capacitor and the positive side to the other side of the capacitor, which are two 500 picofarad capacitors, which are rated for around 15 kilovolts, I believe. So together they can handle 30 kilovolts. Here's a little fan that's connected to the battery, and then here is the spark gap. Spark gap now is around 5 millimeters wide, so it can generate a lot of voltage. Basically 3 kilovolt per millimeter, so 5 millimeters would be 15 kilovolts, but that's a rough guessing. Now here I've got a grounded coil. Let me put a safety clip on this. So I've got this copper rod, and that is where I discharge through. So the positive side of the capacitor is at this time earth grounded. So the negative side charges up with negative voltage, and it passes through this copper rod to the spark gap, which is then on the other side grounded. So the capacitor discharges through the rod to ground. So we have a negative voltage that is built up by the flyback into the capacitor bank, and when the spark gap triggers it, it discharges suddenly within around 40 nanoseconds. Now around this I have a tube, it's a coil, and I've grounded it on one side. So basically this is another capacitor, because this will be charged up negative to negative 15 kilovolts in theory, and this will be earth grounded. Now the other side of that coil is probed by the blue lead. It's a high voltage probe, and then I've got an orange high voltage probe here, which is loose coupled. It is not touching the metal, but it's nearby, and thereby it will sense the fields that are being presented as an electrostatic field that is being built up and discharged. Now, this is a DC discharge, and these discharges are extremely noisy. I've got a scope over here. I'm gonna set it to auto trigger, and let's just run it. Prepare for the noise. Oh, let's first take off the safety. That's a good one. Everything's safe. Yeah, I believe so. Here we go. Really, that noise, it's deafening. And actually, I've got earmuffs for that. And I didn't put them on because I also wanted to experience that noise. Yeah, that's a good one. All right, one more time. Here we go. Yes, that's a good recording. Okay, I'm going to show you the scope shot and we'll be able to zoom into that. Okay, here we've got the scope shot. As you can see, the orange is the trigger signal and the blue is the coil. So directly probed on a coil. I'm going to zoom in and first we'll take a look at those orange ones. So this is loose probe. The voltage isn't correct because if I would grab that, I would probably measure something like 12 to 15 kilovolts. Now remember that this is the discharge. So let me zoom in a little bit further. So here is the discharge and then it starts charging up to a negative voltage again. So I've got a slow charge to negative voltage, which is then abruptly discharged, and it's really quickly. Let's zoom into that discharge. Let's see how quick that is, because it's really quick. So here you can see the scale. I've got 80 nanoseconds per division. So this is 80 nanoseconds, and the discharge takes place in, well, less than 80 nanoseconds. It starts oscillating then, so there will be a little bit of overshoot. So actually, I would say the average is around here, which is 40 to 50 nanoseconds discharge. And that is that 12 to 15 kilovolts. So that is a massive dV/dt. Very strong. Now let's take a look at the blue signal. The blue signal is the probe coil. It is very high in frequency. Let's zoom out a little bit and look at that signal. And that's a little bit weird to me. So you've got a ring that dies off, and that is to be expected. But there's something strange about this. Let me turn off the orange and let's center this one, and maybe we can scale it a bit. So in the start, we have a negative to 0 discharge, and this also goes from 0 to positive. So that is the same polarity. That's all good. But the weird thing is, it then goes down, becomes less negative. It goes up, it becomes more, and it goes down and it goes even more. Let me scale that back. You see how that rings? Let me zoom in a little bit more to that front of that oscillation. So here we start. We go up, we go down, we go up higher, we go down higher. So actually we have a ring up. That's strange. Why is it ringing up? It should be ringing down. It should get its maximum amplitude from that shock and then ring down, but it doesn't. It rings up. Then it's not sure what it's gonna do, but then it decides, yeah, I'm definitely going to ring down, and it's ringing down. And then the frequency changes, at least, because in that period here, I can't see that high frequency oscillation anymore. It starts out with a third harmonic, and then it goes 3 octaves down. It slowly transforms into a slower vibration. That slower vibration dies off. I'm gonna look for a different discharge. Maybe there's one that rings a little bit better. So I've got it zoomed in now, and again you can see that the oscillations start out really quickly and then become a lower frequency somehow, and then they die off at a higher frequency again. So there is this weird transformation of very high third octave of that 8 megacycles, and then it goes to the becomes faster again. It's so weird to me. Now let's put in that orange signal again. So here you can see what is actually happening together. That discharge happens, and the ringing of the coil is even quicker than the discharge. That is weird. It's a higher harmonic that is responding. The coil responds with a higher harmonic. Very interesting, this. Conclusion. Tesla was clear. It was not an electromagnetic effect. Instead, he used powerful electrostatic effects. the slow transverse buildup of the high voltage electrostatic field, which then was suddenly and very quickly discharged without polarity reversal, caused a longitudinal shock wave, which he later called radiant energy. This caused a resonant mode in the secondary that was electrostatic in nature, but it was a dynamic form of electrostatic resonance. This also produces higher harmonics and impedance effects. You can now join as a member on my YouTube channel. I intend to produce member-only educational videos to help you start with your own research. The first video will be a summary lecture of the essential topics which I've mastered in the past 8 years of my research. So join now! You can also support my research by donating to my PayPal, which is listed below, or you can scan this QR code. Thank you for watching and see you next time.